I'm going to work out example 8.9 from the textbook, but a little bit differently than it was posed. Example 8.9 is about two air track gliders that collide elastically, which would mean that they bounce off one another and conserve kinetic energy. However, as a little practice, I'm going to solve this problem assuming that the air track gliders collided in a perfectly inelastic way. So in a perfectly inelastic collision, two or more masses come together, and after the collision, they're all stuck together and they move away at a common speed. So to get started, I've drawn a before and an after picture. That's always the first step for conservation of momentum problems. So initially, glider A is moving to the right at 2 meters per second, and glider B is moving to the left at 2 meters per second. One thing that I'm going to do that's a little bit different than the book does is I'm going to deal with velocities as being magnitudes and assign their directions by arrows and with plus and minus signs. So here we go. Because this interaction conserves momentum, the initial momentum and the final momentum of the system has to be the same, which would mean initially the momentum of A plus the momentum of B has to equal the momentum of the two things moving together at this common final velocity. So the only thing to be careful of is to assign directions for the various quantities appropriately. So I want to point something out here. First of all, I put the minus sign here because the momentum of glider B is to the left. And I assume this is plus because I really don't know the direction. And if you don't know the direction, assume it's plus, and if the answer comes out minus, you'll know you just guessed wrong. So what's left really is to solve this momentum equation for the final velocity of the gliders stuck together. And that's really not too hard to do. I will also point out that if you read section 8.3, you'll simply see an equation like this as a numbered equation, but I don't think it's useful that you remember it because it's just as easy to do a before picture and an after picture. Use conservation of momentum to generate the equation that you need to solve. So I can do this one algebraically in my head if you want to pause the video and do it for yourself and then check your work. Yeah, I realize it's pretty boring to watch that, but nevertheless, that's what we got. So what's left here is to simply plug in some numbers for the various things in order to get what the final velocity of the gliders is. So if you plug in the numbers that are up here, I think you'll verify that you get 0.50 meters per second, and it comes out plus. So we can interpret this result by saying we guessed right that the final velocity of the gliders now that they're stuck together is to the right, and we got the magnitude of the final velocity as well. Now one thing that's worth checking is kinetic energy. So an inelastic collision like this is not supposed to conserve kinetic energy. So let's check to see if that's the case. What I want to do is calculate the initial kinetic energy and also calculate the final kinetic energy and then see if they're equal. And if they're not, I'd like to know by how much the kinetic energy changed, because the change in kinetic energy would be any non-conservative work that's done. Okay, so the initial kinetic energy is the kinetic energy of the two masses. And I don't think you're going to make any mistakes here, except possibly for one. And that is, you might think that you got to make this minus because you know that this glider is moving to the left. But I want to remind you that kinetic energy is not a vector, and all of these speeds are squared. So you always add kinetic energy. So if you plug in the numbers to this, you could pause the video and verify, you get 1.6 joules unless I've made a mistake. Now after all is said and done, the kinetic energy of the pair of gliders moving together would be calculated like this. You would 1/2 mv squared, but the mass is the sum of the two masses, and they're moving at the same common final velocity, which is 0.5 meters per second. And if you plug in the numbers here, you get 0.1 joules. So as a matter of fact, the final kinetic energy is a lot less than the initial kinetic energy. In fact, their difference is 1.5 joules. So nearly all of the initial kinetic energy was lost by non-conservative work. Now in the context of a car crash, you could see where that non-conservative work would come from. If cars crash, fenders bend and glass breaks, all of that is an example of non-conservative work. Those things aren't springs, so I guess the important thing to keep in mind is the internal forces that do all this non-conservative work don't change the momentum of the system. So the internal forces always add to zero, so the force on glider A by glider B is equal and opposite to the force on glider B by glider A. That much is true. They cancel out, so momentum is conserved, but those forces in this case surely do a lot of non-conservative work.